let's continue. Chairperson. Oh, see you. Can you call the people now? Two. So is this on? Come on. I have no respect for the lecturers here. Okay, let's continue. Oh, this is very strong now. Eh? Wow, new batteries, amazing. let's put it here. Let's continue. So this is the way of writing the effective Hamiltonian. All right. As you see, I did nothing special. Again, I just reshuffle the coefficients of my tensor as a vector, and then this is exactly a quadratic equation in the coefficients of the vector of the tensor. All right. Now let's do the same thing for the denominator. This means for the norm of the state. So similarly, for psi times psi, well, we are going to have the same thing, but without this box in the middle. All right. So, well, we just do it. Psi, psi. This is 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. That's a ket. This is the bra. 1, 2, 3, 4, and 5. So this is psi, ket. This is bra. And now we are going to do the same story. This is AI, A star, well, AI star. And we just detach the tensors at side I and write this in the same notation as vector A I daga times some normalization matrix times AI. Exactly, this is what I'm going to show now. So this normalization matrix, I just need to do the same thing here. So here, the effective Hamiltonian is all the tensor network except these two tensors. Okay? It's whatever is in the middle. So here is the same story. It's all the tensor networks except these two tensors. It's going to be my normalization matrix. All right? So just to be consistent, n alpha beta is going to be 1, 2, 3, then nothing here, 4, 1, 2, 3, then nothing here, 4, and of course there is an identity in the middle, right? And this is going to be index beta, and this is going to be index alpha. All right? The same thing, but without the Hamiltonian. That's it. This looks strange because this is disconnected. Well, it's true. It's disconnected. In 1D, with open boundary conditions, this normalization matrix has 3 disconnected pieces. One of them is an identity. If we had periodic boundary conditions or we were in a 2D system, then no, then everything will be connected. All right? But a priori, in 1D with open boundary conditions, it's disconnected, and it makes life easier. All right, so let's rewrite our optimization problem. And we are minimizing this object, expectation value of psi. This can be written as A I daga times effective h times a at site I divided by a I dagger times normalization matrix times ai. Now, minimizing this equation is equivalent to minimizing the numerator with the constraint of the denominator. The denominator is just a normalization constraint, all right? So this is equivalent to minimize the following functionals. Minimize the following functional. Let me call it f just to make a distinction with e. So this is, you know, the expectation value of h minus lambda times psi, where this guy is a Lagrange multiplier. Actually, if we want to be very precise, this is psi minus 1. All right? These two optimizations are equivalent. I just impose a normalization as a constraint. Right? Now, I can write this in terms of effective Hamiltonians and so on here. Let me do it here. So this is going to be ai dagger times h effective times ai minus lambda. And then we have the constraint, which is ai dagger times normalization matrix times ai minus 1. And here comes part of the magic of DMRG and the reason why we do this optimization side by side. This is a quadratic problem in the coefficients of the tensor. This is great. Okay? So it's not cubic or quartic or anything strange. It's quadratic. So, you know, if it has a minimum, it has a minimum. It's like a parabola. All right? So we can really optimize this directly and find the solution.
So,
yeah.
Could you clarify the dimensions of these A vectors?
Yes. Yes. Yeah, yeah. So AI, this is this guy, no? With all these indices together, right? Now this dimension goes from 1 up to D, 1 up to D. This one in the middle goes from 1 up to P. So you know, this is a big index, let's call it beta, that goes from 1 up to P D squared. So it's a P D squared dimensional vector.
So then how do we see dimensions of the H effective?
Oh, the dimension of H effective is going to be the same story. So H effective of beta alpha is such that, well, beta and alpha go from 1 up to P D squared, because it's the same vector spaces. The indices are joining, you know, these indices are the ones that are connecting with these indices. So they must have the same size. Okay? So this is also a P D squared times P D squared matrix. So the indices here are referring to the same vector spaces as in here.
This is essentially like the H I alpha beta, because now you add brackets and single out the I alpha signs.
Yeah. So this is a P D squared times P D squared matrix. So P D squared times P D squared. And this one here as well. So this is P D squared times P D squared. Yeah. The bigger the D, the bigger the matrix, the more coefficients. Okay? Yes?
So what do you actually do when John together?
Oh, what do I actually do? Well, if you do it in MATLAB, there is a function that does it for you. It's called a reshape directly. But in Python, there is also another function. But this, in practice, this is, it's also called reshape. Yeah, it depends on yeah, on the packet, no? But in practice, if you had to do it in Fortran, like old school, no? Well, this is just a combined index. Okay, so you know, instead of, you define all the possible values of this index as all the possible values of these three different indices. You have a table. Okay. So normally, it's just a way of rearranging things in the. I mean, actually, in the computer, physically, nothing happens because it always stores the things in the same way, but the way it calls the different components changes. Okay, the pointer, let's say. More questions? I see there are some Python experts here. Not like me, I'm struggling with learning Python. Nowadays, everybody likes Python, I don't know. I'm getting old. Very good. So, yeah, this is a quadratic problem, okay? And it's a quadratic problem for p times d square parameters. Now, well, the minimization is very simple, okay? So, for instance, let's take the partial derivative of f with respect to the vector ai daga equal to 0. And this, what gives you, from here immediately you can read that this is the condition h effective times ai equals lambda times n times ai. That's it. This is a problem that we need to solve. Let me put it in red because it's important. In practice, we don't need to call any minimization function. We can do the minimization analytically. And the problem that we need to solve in the end is this thing. What is this thing? Those of you that are experts in Python. Huh? It's almost like an eigenvalue problem. No? This is called a generalized eigenvalue problem. It's finding the generalized eigenvalues of matrix HF, where I have an extra matrix on the right-hand side that is a normalization matrix. Okay? Huh? Oh, this I don't know. Possibly, yes. Yeah. So this is a generalized eigenvalue problem. Okay? Now, this problem, they typically don't teach it in courses of linear algebra, but it's almost as easy to solve as a standard normal eigenvalue problem. And in all the linear algebra packages, there are functions and methods to solve it very efficiently. All right? So here is the strategy. I just compute HF, I compute N, solve this generalized eigenvalue problem in my computer, look for the ground state, okay, of this guy, and this will be the one that is minimizing this energy, and then move on. Okay? So once I find the generalized eigenvector, that's this vector, then I reshape it back as a tensor, and that's the coefficients of the tensor. All right? So in practice, we are not minimizing anything. We can do the minimization directly analytically, and well, we need to solve a generalized eigenvalue problem. Okay? So well, those are the next steps. Then the rest of the algorithm is very simple. So, you know, in tensor network methods, we spend the life doing singular value decompositions and solving generalized eigenvalue problems and systems of linear equations. That's 99% of what has to be done. Okay? Good. So then step 5 is solve the generalized eigenvalue problem. And, you know, find the optimal AI. As a tensor, okay? That's the solution of the generalized eigenvalue problem. Then we replace this tensor at site I. At site I, and then move to site I plus 1, and repeat. So once I find the optimal tensor at one side, I just move to the next one and repeat the same story. I recalculate the effective Hamiltonian, I recalculate the normalization matrix, put this into my solver for generalized eigenvalue problems, find the optimal tensor, replace it, and move one more step, and so on. Yeah. Oh, I didn't say this converges. I'll show you. We'll discuss this in a second. Okay? Yeah. More questions? Yeah.
So we calculate the generalized eigenvector
Yes.
and then we place it in that equation.
Yes. No. So we compute the generalized eigenvector. Okay. So once you have AI, you need to move one step forward. Okay, and recalculate everything. So
And there are multiple eigenvectors.
yes, you have to look for the one for the ground state, the one that minimizes lambda.
So lambda is real.
Yes, lambda is actually, well, if you pick up this equation, you can see that lambda is actually this expectation value. Okay, so you have to you have to find the ground state or generalized lowest eigenvalue of this. Okay. Well, so we move to side I plus 1, and then step 7, which is the last one, is sweep back and forth and check convergence. Okay. And this is it. This is the MRG. It's a variational optimization side by side of a matrix product state. Well, because in 91, Steve White found this method without MPS. And he was just thinking about renormalization. What he was doing was, okay, I have a many-body system. I compute the ground state for a small system. And then I join it with another one, add the interaction, and then renormalize. And the renormalization, what he did was to keep the maximum entanglement between the two subsystems that he was joining. Okay? And then he had to play with the Smith decomposition and so on, right? But he never thought about an MPS. Now, I think it was in 95 that Oslund and Romer realized that this is exactly what he was doing. Yeah. It's another way of rephrasing the method. I think it's slightly more efficient like this. It's absolutely equivalent, but it's a bit more efficient like this. And now, when you see it like a variational method, you understand how to go to other systems. Yeah.
I don't understand how this H-connected looks.
Oh.
So you still have to construct this huge diagram, right?
Yes. Yeah. I still didn't tell you how the Hamiltonian looks like. So maybe. So I say something about convergence, and then I will tell you how to compute this Hamiltonian. Okay. Good. So what is the typical behavior here? So typically we have this. This is the number of steps, okay, or sweeps. And this is the expectation value of the Hamiltonian. And normally one starts with a given bond dimension, let's say d equals to 10, and find something like this. And at some point you can optimize more your wave function. Then when you arrive at this point, you increase d, all right? And then you find this. D equals 20, d equals 30, d equals 40, and so on. So you optimize, you keep doing sweeps until convergence for a given bond dimension, and then you increase the bond dimension to allow for more parameters, and then you go down. And since it's a variational method, and all the calculations are exact, there are no approximations in computing these, as I will show you in a second, the energy always goes down. It can only improve after every step. Worst case scenario, it remains the same. Okay?
It's just like the variation method, right?
Yeah.
More parameters.
It's a variational method, but with more parameters. Yeah. So that's a typical plot of a DMRC calculation. You see the energy going down, 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 and at some point you just, you have a criteria and you say, hey, stop here because, I don't have more memory, or this is already the convergence that I want, or whatever. All right? Good. Now, let me tell you of a couple of remarks. Well, the first one is how to compute the Hamiltonian, okay? Well, how to compute the effective Hamiltonian? I mean, this looks like very complicated, no? But the point is that H, normally, at least I didn't see any exception, all Hamiltonians of locally interacting quantum many-body systems, they can be described in terms of something called a matrix product operator. Or an MPO, okay? What it means is that, instead of dealing with this very big tensor, there is actually a way of writing the Hamiltonian as an operator that looks like a matrix product state, okay? Something like this. As a tensor network. No, it's always the case, yeah. It's always the case. The problem is that there is not a general theory about it, but everybody knows, well, not everybody, but the people know how to construct them, essentially in all cases, all right? Now, example, well, here there is another bond dimension that we are going to be calling D prime. Yes? Oh, no, and also non-local, even for long-range interactions, and yeah. So this is for 1D, okay? Now, example, and I write the example, and then I let you think about it. It's this Hamiltonian of the transverse sterilizing model in a magnetic field, the one that we did when we were talking about quantum phase transitions. Okay, sigma I plus 1x plus h sum over I sigma iz. How do the tensors of the MPO look for this Hamiltonian? Well, let me just write them here. And then I let you play with the coefficients during your trip back, all right? So the MPO is given by the following coefficients. Let's see. So 1, 1, this is the identity matrix. I'm going to fix these bond dimensions. And then since what is left is a tensor with 2 indices, what remains here is a matrix. Okay? So I'm saying that this matrix is the identity. How was this? 1, 2 is equal to sigma x. 2, 3 is equal to sigma x. 1, 3 is equal to h sigma z. And then 3, 3 is equal to the identity. And 0 otherwise. This is an example of an MPO. I think I got it right. 1, 2, 2, 2. 1, 3, 3, 2. Yeah, it's fine. This looks like black magic. Okay?
Is the number labeled here
So here. No. Oh, no. What do you mean the sequence of the Pauli matrices? No, what this is meaning is that this is the tensor of my MPO, this guy. And this has coefficients alpha, beta, ij. Alpha, beta, so let me call this tensor T, okay? So this is T of alpha, beta, ij, okay? So when I say 1, 1, ij, this is T of 1, 1, ij, and then I'm saying that this is identity ij, the delta, okay?
Right. I mean, like, are you using the same Hamiltonian right on the left?
This one, yes.
Yeah, so when you choose alpha beta, are you choosing the self-index I?
No, because it's an operator. So these indices, I left them open, okay? So in the end, what I'm going to be doing with this is I'm going to be doing this contraction. Okay? And if I do this contraction, what I get here is the coefficients of this Hamiltonian. Okay? That's it. So, this Hamiltonian can always be written using the notation that we did the first day. So I1, IN, J1, JN, C, I1, IN, J1, JN, and then I1, IN, J1, JN. So what I'm finding is these coefficients. It's the same as for a quantum state, but for an operator. Yeah.
So like V1 is 1 over h sigma z?
Which is 1 over h sigma z? No, this is h.
That's h sigma z. What's the 3 1?
No, there is no 3-1. 3-1 is 0. 3-1 is 0. It's tricky. It's a bit of an art to realize how to write these things. But the idea is that, well, you see, let's imagine that I start with a 1 on the left. Then I have a 1, 1, 1, 1, 1, always identities. At some point I hit a 2, then I have a sigma x. But if I have a 2 on this side, the only option is that on the next side I have another sigma x, because it's the only one connecting with a 2. And then I have to connect with a 3, and the only option for 3 is an identity, and then 3, 3, 3, 3, 3. So this gives me an XX interaction, all right?
You have to do the separating the matrix first.
Yes.
Okay.
Yeah. Exactly. Okay? So this is this Hamiltonian written as a tensor network. Okay? Yeah.
Obvious that the prime is free.
No. It depends on the range of the interaction. So if you have long range interactions, this D prime grows with the range of the interaction. Okay? So you cannot, I mean, you can do next to nearest neighbors and so on, but if you have something like a polynomially decaying interactions, then you have to truncate this D prime at some point, because otherwise it just grows up. All right? More questions? Well, they were very creative. Yeah, but then they realized there is some theory based on sending signals and so on, but I don't like it. So it's more, you know, getting used to this. In 1D, all the MPOs look very similar to this. Okay,
It's
so.
only like much easier to work with, I don't know, with the sigma.
Yeah.
If you work in
No, but you cannot work with this, because then you will be in this picture. Okay, so you need to be able to decompose this as a tensor network in order to make the algorithm efficient. Yeah. Shh. Yeah.
Which would be harder if you increase the matrix. Much harder.
No, but well, I mean, no. If you have two-dimensional systems, there is a generalization of this. So this does not apply directly. There is a way of doing this really two-dimensional. More questions? All right. So think about this. I know this is non-obvious. At least it was non-obvious to me when I saw it the first time, but it's true. So you can write any, think about your favorite Hamiltonian in 1D. Turns out that there is always a way of writing it as a matrix product operator. And typically this bond dimension is not too large. Yeah.
Like for the wave function, we're not always targeted like
Exactly.
but
Yeah.
for operators, it's
Almost always, yes. Yeah. If the interactions are local, then yes. The more non-local are the interactions, then the less truth is this. Okay. So, for instance, if you have, as I said, polynomially decaying interactions, then this bond dimension grows. Okay, and then you have to truncate it at some point. Actually, the way people in the MRG deal with long-range interactions is that they expand it in terms of exponentials, and then they truncate at some point. Okay. Good, so a second remark is the computational cost, which is order n p cube for open boundary conditions. And now what I explained, you can just do it also for periodic boundary conditions. There was nothing special here. And then for periodic boundary conditions is order n d to the 5. No. Well, yes, but typically you don't put it as a parameter here. It's a small. D is typically of the 100, 1000, and then D prime is 3. So
What happened if you compare with the previous like n and d sort of here? Why is it
why is the cube? Because solving the generalized eigenvalue problem is the cube. Yeah. Yeah.
Is this the only way of writing this Hamiltonian?
No, there is a gauge degree of freedom here. Remember that yesterday I said that you could introduce here xx minus 1 and nothing will change? Then there are many ways of rewriting this. Yeah. But this is kind of the more obvious one.
They all give the same result.
Yes. Yeah.
But didn't we have to solve a generalized eigenvalue for vectors that was the size of d cube p?
No, it's not the cube, it's d squared.
So this squared p.
Yeah. So it's p d squared times p d squared. Solving this generalized eigenvalue problem is the cube. Yeah.
Extremely efficient. Okay?
It's very efficient, yes, because in practice you don't need to store this matrix. You know, it's like these methods for sparse matrices that maybe you played a bit with this, so that you only need to store how the matrix acts on a vector, and they scale like the cube. Okay? Good. Yeah, it's super efficient. So people thought about this for 30 years already, and they know really how to do it. Now, for infinite is the cube, and this is called IDMRG. For infinite size systems. And yeah, well, that's essentially it. There are tricks for the stability of the calculation. There are things like working in different gauges. And there is one gauge that works very well, which is the canonical form, the one that I introduced yesterday, and so on. So this is a numerical method. Of course, there are many little tricks here to make the method work, and the people know them very well. So if you take a look at the reviews by Uli Scholbuch that I've put in the Dropbox, he explains them, all of them. Okay, he explains them. He explains everything. There is a way of redefining the tensors of your MPS such that this normalization matrix that is no longer here actually disappears. So if you put your canonical if you use the canonical form of the matrix protestate, then this normalization matrix becomes the identity, and then what you have is a standard eigenvalue problem that is very easy to solve. But of course, you have to recompute this canonical form every time. Okay? Good. Yes. Because for open boundary conditions, all the contractions that you have to do are like this one. Okay? When you want to compute expectation value or edge effective for the normalization matrix. Versus something like this for periodic boundary conditions. Okay? Because this is connecting. Right, I don't know how to put it. So essentially you have to do a contraction like this. This contraction is 2 orders of magnitude more expensive than this. That's it. That's the bottleneck. Infinite is even cheaper. It scales like open boundary conditions, but since it's translational invariant, you only have one tensor and there is no scaling with the size of the system. It's kind of strange. It's an infinite system, but does not scale with the size. Yeah. Yeah.
How do you make use of the symmetries?
Of the symmetries. Which type of symmetry? Translation invariance or SU2 or yeah. You impose it on the MPS. There are ways of making your tensor network translational invariant. Say you put the same tensor everywhere or a unit cell. And then there are ways of making your tensors SU2 invariant, for instance, or Z2 invariant. And this is a whole theory of symmetric tensor networks that I will not develop. But there are ways of making your tensors invariant under a symmetry group. And then you optimize only over symmetric tensors, right? And well, your algorithm works better.
So you use the symmetries in the beginning of the code?
Yes. Yeah, from the beginning. Yeah. For instance, the people that study SU2 invariant systems, they implement SU2 DMRG, they call it. So the ansatz, the MPS is directly SU2 invariant. It means that if you apply a matrix of SU2, the state does not change, but every tensor also does not change. What happens in the end is that the tensor splits into 2 different pieces, one that is only Klebs-Gordons, and then another one which are the parameters. Okay. More questions? Yeah.
For this matrix product operator implementation, it's always a new node, like new problem, or you can...
It defines your problem. So you are given a Hamiltonian and you say, well, I want to compute the ground state of this. First thing that you do is what is the matrix product operator for this Hamiltonian? This is normally easy to find, okay? And once you have this, you start the algorithm, okay? Because for the algorithm, you need to write it like this, because otherwise the contractions that are involved in computing this effective Hamiltonian, they are not efficient. You cannot deal with this monster. It's too big. You need to break it like that, okay? Yeah?
Are there any ways that you can impose the symmetric or antisymmetric over the indices?
Yes. For instance, for fermions, you can do fermionic focus spaces and impose that they are antisymmetric. Yeah.
So when you change B, you impute it, is there a clever way to set the new parameters?
No, typically one. at the beginning of your calculation, you just start from the ones from the previous calculation. Here, normally, if you have a guess, you use the guess. If you don't have a guess, you start from random. Okay?
From D equals 10 to D equals 20.
You start from the best solution for D equals 10. That's your initial step for D equals 20. You just allow to grow the bond dimension a bit more. Okay? More questions? Good. Yeah. In the what? Yes, yes. So this is for ground states of quantum systems. But for classical statistical mechanics in 2 dimensions, the people develop methods that are very similar to this, or essentially the same, but it's the classical version of this. So finding the dominant eigenvector of a 1D transfer of a 2D transfer matrix, for instance. This will solve the 2D classicalizing model, all right? Yeah, the people did exactly the same thing for classical systems as well. Yeah. Yeah.
So in the renormalization, the idea is to integrate out these degrees of freedom that we are not interested in.
Yeah.
How do we see it here?
It's a truncation in entanglement. We fix the amount of entanglement up to a given number, capital D, all right? And this fixes the total amount of entanglement entropy that I can have. And this is like saying, this is the number of relevant entanglement degrees of freedom is going to be upper bounded by the bond dimension. All right. It's not easy to see in this picture why this is connected to renormalization. For this one, you'll see the original formulation of Steve White. But there you see that exactly the renormalization is truncating in entanglement. All right. To say, okay, I'm going to keep up to this level of entanglement degrees of freedom. Yeah. More questions? Okay, so in the last 5 minutes, let me show you some slides. Okay, this is the MRG. Now I want to tell you about all the things that I didn't have time to explain you, okay? But very quickly. You can do much more with tensor networks, okay? This is just the beginning. So, and you will be able to see my super fancy pointer. Okay. Well, it takes a while until it warms up. Hello. It's warming up, yeah. Okay, well, so we talk about matrix product states here. You could say, wow, this is very complicated. Well, look at this picture. we just did this case in here, okay? You see, wow, this is super fancy, eh? Okay. Good. So we did MPS, that's a case 0 tensor network, and you can already see that there is some algebra, but it's very useful. Now, people also generalize it to 2D. This is example of a PEPS, or project entangled pair states. One can also do variational methods here. This is a 3 tensor network. This is a 1D mera. This is a very interesting tensor network because this is the one that matches critical systems in 1D. Remember that I told you there is a lock for the entanglement of a quantum critical system in 1D? It means that the correct structure of entanglement is not an MPS, it's a mera. And I will show you in a second why it's a mera, but mera, I mean, there are ways of generalizing this to be more complicated situations. This is a branching mera. Now imagine doing a variational optimization over this guy. Okay, there are people that have done that. So some PhD student. Okay, these guys are, these structures are exact in many cases. We have many examples, like strict net models, topological models with topological order, and so on. We know exactly how the tensors look like. And when we don't know how they look like, well, they are just an ansatz for many body wave functions. Good. So you see that here, you know, the only limitation is your creativity. Depending on the structure of entanglement in your quantum state, you have to more or less understand what is the correct tensor network structure. All right? Yeah.
So this triangle and the square are different.
They are different things, yes, but I will not explain them here. They are unitaries and isometries. Yeah. But in the meta, the tensors are funny. Okay? You have to impose constraints on the tensors. They are not just arbitrary. Oh, you were first.
How long does the calculation?
I don't know the scaling. So the scale. I mean, the scaling for MPS is very efficient. For 2D PEPs is of the order of D to the 10, I think, when you put everything together. But one can still do it because for PEPs the bond dimension that you need is very small. Three tensor networks are like MPS, is cubic. The meta, I think, is order d to the 8 or something like that, so it's very expensive. And the branching meta, I really don't know. It's very, very expensive. Yeah.
But this is all using DMRG, so just a different answers.
It's a different ansatz. You do the same.
DMRG.
It's the same DMRG. Yeah. But they don't call it DMRG. It's a variational.
Okay, so basically this is just saying that I'm doing variation method by parameterizing my wave
Yeah.
function very near
Yeah.
tensor network
Yeah.
size.
But the idea of the tensor network is that you are putting the entanglement structure in the ansatz, and then if you have the correct entanglement structure, that's 90% of the wave function. Yeah. More questions? Yeah.
So if entanglement's proportional to area, some area law, could it be like you use area law somehow to simplify some approximation?
Yeah. Well, you see the type of entanglement that you have, and you think, okay, this should be an area law. Or a correction to the area law. Now, which tensor network structure is giving me this? Okay, and this is how people came up with the meta. This I will show you in a second. That with this, you have a logarithmic correction to the area law. Okay, good. So does this work? Well, yes. Here is an example of the 2D Hubbard model, which is a very complicated problem. And this is an old slide. This is Matthias Treuer, that you know he's a very renowned computational physicist now working at Microsoft. No? At 2015, he said, yeah, you guys really made it with this infinite PEPS calculation, which is like infinite DMRZ, but in 2 dimensions with another ansatz. Philippe Corbeau was actually able to compute the best variational energies for the Hubbard model, much better than with any other method. So yeah, it works. And this is already an old slide, so nowadays it's working even better. Now, what about 1D systems and critical points? You were always asking this question. Turns out that the correct structure of the tensor network is not an MPS, because the MPS has a 1D area law. The correct structure of the tensor network is this monster here. This is called a meta, where these are the physical indices down here. This is the physical dimension, all right? This is my one-dimensional space. But now the tensor network expands along an extra dimension that is called holographic, okay? So there is an extra holographic dimension that takes into account the different scales of the renormalization group, right? And well, turns out that there is a physical motivation for this that I won't explain, but if you compute the entropy of this guy, you have a block of length L. How many lines do I have to cut to, separate the block from the rest of the system? Well, it turns out that it grows like this. It expands in this holographic direction. An entanglement at the end is the boundary or the area in the holographic geometry. So it's the number of bounds, it's upper bounded by the number of bounds that you cut, which is the surface of this boundary, times the entanglement per bond, which is log, I was saying log d. In this slide, I'm using chi instead of d. But this is the same law that we have been seeing here for MPS and so on, all right? Now, if you do the counting, turns out that there is log L layers here for a block of size L. There is a constant contribution at every layer. So you have that the prefactor is log chi, and this size of the boundary in holographic space is log L. And this is exactly what you find for critical 1D systems. You remember this result from conformal field theory that I said the entanglement grows like C over 3 logarithm of L? That's it. It's the entropy of a meta. All right? Now, this is just to show that the meta actually works for critical systems. You have polynomially decaying correlation lengths. The meta has infinite correlation length, not like the MPS, that is infinite. Some people have connected it to quantum gravity as well. Did you hear about the ADS-CFT correspondence at some point? So some people understood that the meta is actually a lattice version of ADS-CFT, which is a holographic correspondence in quantum gravity. The point is that the way you compute the entropy on the meta is exactly the way you compute the entropy on ADS-CFT. This was done by 2 Japanese people, Ryo and Takayanagi. And this is pretty interesting because when people propose the meta, we're not thinking about quantum gravity at all, right? They were thinking about what is the entanglement structure of a quantum critical system. And now the quantum gravity guys come and say, hey, look, you just did a lattice discretization of what Juan Maldacena was doing with string theory. What? So, this is one of those interesting connections. But it's interesting because, these people in quantum gravity now do things like this. Imagine that we have this crazy tensor network. Now, we put we just cut it like this. then this is almost like an MPS, but with some internal structure, so it has a finite correlation length. And now is a question for you. Can you imagine what this is? It's a black hole. It's a model for a black hole in anti-de Sitter spacetime. No kidding. It works. So Maldacena and Susskind and these people, now they are working, they are thinking a lot about entanglement and tensor networks precisely because of things like this, right? So this is, it's a very interesting connection, and we still need to understand what the hell is going on, what this means, okay? But just to show you that there are applications of tensor networks much beyond condensed matter. Actually, every time I give this talk, I have to update this slide. These are just some fields where tensor networks are just showing up. We were just talking about the strongly correlated systems, okay? But you see, even in artificial intelligence, in, I don't know, quantum gravity, in linguistics also, I mean, there are many applications of tensor network states. Essentially, anywhere where you have a structure of correlations, you have a tensor network. All right, that's the message that I want to transmit. Of course, in quantum many-body systems, but I don't know, neural networks, yeah, they are also tensor networks, okay? Yeah.
Where is the finance?
Oh, no. No, that one is a secret of my startup. No. There are also applications. I mean, in finance, there are many optimization problems, okay? And for those, you can apply things like MPS and so on. Yeah. All right. Things that I didn't explain here because I didn't have time that have to do with quantum information condensed matter. Well, topological order. But you had several lectures on topological order here. No? The point is that in topological order, you have a long-range pattern of entanglement. Also, quantum simulations. One can do very nice simulations of quantum many-body systems using optical lattices or trapped ions or Rydberg atoms. Of course, quantum computers. Have you seen this picture before? Yeah. This is the IBM quantum computer. This is just the fridge. Okay. The quantum processor is down here. Right, and it's super tiny. This is made of superconducting qubits. It's like the one that Google used to make this announcement on quantum supremacy at the beginning of the week, right? And and just to finish some advertisement, we are working at the IPC in many different problems at my group, right? On quantum computing, quantum information, tensor networks, strongly correlated systems, and so on. We are here in San Sebastian. Also, Sebastian is in San Sebastian. You can see that we are almost French, but we are not French, okay? Don't be confused. We are just 20 kilometers from the border. That's where we are. It's an interesting place, okay? Yeah, you can go surfing, you can go eating. Yeah. And we have open positions for PhD, master, and postdocs, or even visitors. So if you want to come for whatever, just send us an email, and you are welcome. Okay? Yeah, thank you.
Any more questions?
So are you really working on the black hole?
No. No, I thought about it for a while, but no. No, it's most of the people that are contributing there are the string theory people, actually. Yeah, it's easier for them than for us. Yeah. More questions? Yeah.
Are there string theorists in psychology?
No, not the string theories, but there are cosmologists. There are people doing cosmology, yeah, and black holes, yeah, but not the string theory. Yeah.
So you said that to construct a good structure, you need to know the entanglement, but
Yes.
to know the entanglement, you need to know the waveform.
Yeah, essentially.
Then in case of this one, the critical point, then you kind of know it, but
Hmm.
like in general,
You need to have an intuition. So for instance, if you have a 1D Hamiltonian at a critical point, then you say, well, I know from these results in conformal field theory that it's very likely that the entanglement entropy SK is like a log. Okay? So, you need to have these kind of intuitions.
in any case, you can only guess something.
Yes, you have a guess, and then you put the answers. And if it works, then it's a good guess. If it doesn't work, then it's another answer. Yeah, that's how life is. Yeah.
Has this been applied for the fractional quantum states?
Yes. Yeah, this has been applied for the fractional quantum Hall states. So there are works by Frank Polman and Nicolas Renaud where they put, there is a way of actually parameterizing the state on a cylinder and then simulating it with an MPS by slicing the cylinder. It's like a quasi-1D system. Yeah.
Let's say that you manage to choose the right tensor network and manage to calculate this DMIG nicely. Is there like any nice transformation that will give you back to some kind of a more representative profile?
Well, there is no more representative wave function than the MPS, okay? Well, yes, in some cases, yes. So if you want to look for, I don't know, Gaussian state of fermions, or yeah, there are mappings.
For example, if you are in a canonical MPS thing, then you basically know that you've been doing symmetric composition.
Yeah.
It may be incredibly hard to go back, but in principle.
Yeah, no, but the point is that from the MPS you can compute everything. So whatever thing that comes to your mind, there is always a way of computing it from the MPS. So in the end, it's like, well, why do I need any other representation? No? So, yeah. But yes, there is. Yeah. More questions? Yeah.
Maybe we can talk about this later, but could you discuss, I know there's different measures of entanglement,
Mm-hmm.
and so could you discuss the drawbacks and advantages of some of them?
Yeah. So for bipartite entanglement, there are there is the entanglement entropy. There are the Renyi entropies. It depends. Each type of measure. Remember that for a measure of entanglement, we had to impose several constraints. Okay. First, it cannot increase under local operations and classical communication. That's number 0. And then on top of that, okay, I want it to be continuous. Right. So the Smith rank cannot be because it's a measure of entanglement, but it's discontinuous. So if you want a continuous measure of entanglement, you can have the entanglement entropy, the Renyi entropies, or others. Now, if you want to impose other constraints from quantum information, like a strong subadditivity, which is an inequality that is very useful, then the only one that remains is the entanglement entropy. All right. Now, in practice, when you have to do numerical calculations, the entanglement entropy is not necessarily the one that is more efficient to compute. So the Renyi entropies are actually easier. So in many numerical calculations, you actually see the Renyi entropy, which has a very similar behavior to the entanglement entropy. It also has these scalings with logs and so on, but the prefactor is a bit different. Okay.
For example, I know there is negativity,
Yes.
which is a direct constraint on the estimator,
Yes.
and so why is this not...
Yeah, it's also useful. Yeah, the negativity, the concurrence, these are measures of two-side entanglement, and people have also used them. Yeah, it's like, but the negativity is like the entanglement entropy between two different sides and the rest. Yeah, it's very similar. So it's possible to compute it, but essentially they don't give more information than the entropy. Yeah. More questions? No? Okay. So final remarks. I've been told by Sebastian that I'm in charge. First, you have to fill in this form, okay, about the evaluation, and remember to give it to me, and I promise I will not look what you write about me, okay, because I have to bring this to Sebastian. Second, I think lunch today was at 12, no? Just remember that. Well, also remember to pick up your posters, to leave your room before 9. To pay all the drinks. Did you pay all the drinks? Yeah, well, okay, we'll see. And then what else? Yeah, concerning my lectures, I will put these slides and also my notes scanned in the Dropbox today. It's an old version of the notes. There are some typos. Feel free to find the typos. Okay, that's an exercise for you. And I will also put you exam if you want to do it, okay, as a summary of what I've been explaining. And yeah, I will do it this afternoon together with some more papers. Yeah, yeah, and that's it. So I hope you learned many things during these 2 weeks and made new friends and had a lot of fun. That was the idea. And yeah, have a nice trip back. And I wish you a lot of luck in your career. Yeah. So yeah, see you.